Today's lecture will be brought to you by the numbers 18, 6, and the letters C and O. Right, that is about all you need to remember and apply in order to be able to do metal carbonyl compounds. To stick to our 18 electron rule and to remember that you cannot have a number, a steric number greater than 6. So this is the number of electrons, this is the number of ligands, and with those two pieces of information we can do metal carbonyl chemistry. So the next 50 minutes or 40 minutes or so are almost entirely superfluous because everything follows from those two statements. Having said that, let's test the theory, shall we? So we're looking for a real transition metal, and so a real transition metal, I mean something between, say, titanium and nickel. So let's have a metal between titanium and nickel. Cobalt, okay? So, cobalt. Which group in the periodic table is cobalt in? 9. So it is a D9 compound, and we're using carbonyl ligands. Now, how many electron donor is a carbonyl ligand? 2. So how many carbonyl ligands do I have to add to 9 in order to get to 18? Yeah, 4.5, but we can't have half a ligand. So let's try with 4, shall we? So if we have a cobalt species with 4 CO ligands, how many electron species is that? It's a 17, yes, we're going for the pieces of paper, that's a spread. It is a 17 electron and therefore a radical species. So what we would need to do is to dimerize this species, and that would give us a 18 electron compound because a metal-metal bond is giving us an extra electron. So all we need to know is that we're aiming for 18 electrons. Now, if you'd gone to a much earlier transition metal, we might have run up against the steric buffers and the limitation of having to have no more than 6 ligands. Here, how many ligands have we now got around cobalt once we've dimerized it? 5. Yeah, I'm glad you said 5. We have 4 CO ligands, and we also have the extra cobalt carbonyl compound itself, essentially as a ligand. So we have no steric difficulties with this compound at all. In fact, so much so that in order to go for a fully sterically saturated compound, then we can actually bridge some of these CO ligands. So we can actually take out these terminal ones and make them bridging. So if I take 2 here and then turn this into a bridging compound, so we have a mu2 ligand here and a mu2 ligand here. Now, if this was a 2 electron donor and it's now sharing itself across 2 metals, what is the electron count of this? Well, cobalt is 9, 3 terminal CO ligands is going to be 6 each, okay? So we're going to get to 1, 2, 3, 18. So this is an 18 electron compound. So what we've got here are 2 possibilities that fulfill our limit of having a steric number of 6 and our electron requirement of having 18 electrons. 2 possibilities. So what happens in nature? Well, both happen. It is perfectly possible to have this compound, which is a normal solid state form of cobalt, dicobalt octocarbonyl, or you can have the compound with all terminal ligands which can be observed in solution. And by the end of this lecture, we'll recognise how to tell the difference between the compound where all the carbonyl ligands are terminal, the one I previously had, and the compound where we have bridging carbonyl ligands. Right. Now, how do you make these metal carbonyl compounds? Well, actually, there lies a bit of a story because the first transition metal carbonyl compound was made essentially accidentally through the contact of nickel metal with carbon monoxide. And when you contact nickel metal with carbon monoxide under completely calm conditions, 1 atmosphere of carbon monoxide pressure and at room temperature, what you get is the formation of a colourless liquid. In the case of nickel, the ion compound is yellow. A colourless liquid. And that colourless liquid is very volatile. It has a boiling point of 34 degrees centigrade. Now, we've mentioned a couple of times, if you can make a convenient compound that is volatile, that means you have the option of distilling it. And if you can make nickel tetracarbonyl, you can then distill it. And distilling something with a low boiling point allows you to get the product very pure. You can then heat it up and it loses the carbon monoxide ligands, and what's left behind is very, very pure nickel. And this process, essentially for making nickel carbonyls in order to purify them, was the founding process for what became Imperial Chemical Industries. Imperial Chemical Industries was ICI. And ICI gave rise, so ICI doesn't really exist, but it was certainly a very powerhouse of the chemical industry in this country for an awful lot of years. Founded on the back of Ludwig Bond's discovery of transition metal carbonyl chemistry. Okay, so nickel is special. Nickel does this at room temperature with 1 bar of carbon monoxide pressure, but it's not the only metal to react directly with carbon monoxide. Iron also reacts directly with carbon monoxide, but there you need somewhat more forcing conditions. So if you use 100 bar or 100 atmospheres pressure and 150 degrees centigrade, then you produce iron pentacarbonyl. And iron pentacarbonyl is yellow. Iron pentacarbonyl can be distilled again, is a yellow liquid, and just like nickel tetracarbonyl, it is an 18 electron compound. And that's the thing we need to say about all of these metal carbonyl compounds that we stressed here. They are 18 electron compounds and they fulfill, therefore, the 18 electron rule. Now, if I was to say to you that nickel tetracarbonyl and iron pentacarbonyl are homoleptic compounds, would you know what I meant? Homoleptic, homo obviously meaning the same, leptic referring to the ligands. A homoleptic compound is a compound in which all the ligands are the same. So the homoleptic metal carbonyls always fulfill the 18 electron rule. Doesn't matter what the metal is, these homoleptic transition metal carbonyls all fulfill the 18 electron rule. Couple of points to note about these compounds. One is that, of course, carbon monoxide itself is toxic. Do we all remember why carbon monoxide is so toxic? Yes, carbon monoxide binds to hemoglobin and therefore oxygen cannot be transported around the blood. So carbon monoxide as an exhaust from a poorly combusting fire is a very dangerous gas to know. So these compounds tend to decompose slowly to give you carbon monoxide, which is a hazard in themselves, but some of these compounds are highly toxic in their own right. So nickel tetracarbonyl is a highly toxic compound, and because it is so volatile, it's actually really quite dangerous. If it wasn't so volatile, it wouldn't be such a big problem, but it's perfectly possible to get a lungful of nickel tetracarbonyl, and that is a dangerous thing to have because nickel tetracarbonyl is a potent carcinogen as well as decomposing to give us CO. Now, that works for nickel and for iron. If you want to make other transition metal carbonyl compounds, it's slightly more difficult. What you need to do there is you cannot start with the metallic element. You have to start with a convenient metal salt. And obviously, what we recognise about these carbonyl compounds is they are compounds of the metals in low oxidation states. The oxidation state in nickel tetracarbonyl is 0. The oxidation state of iron in iron pentacarbonyl is 0. Some of these oxidation states are even negative. And we'll come back to this later in the course. But what you need is a metal salt and a reducing agent, because you have got to reduce the metal to a lower oxidation state in order to make a stable metal carbonyl compound. So if we take titanium, for example, the most convenient starting material for titanium is titanium tetrachloride. You can buy titanium tetrachloride. It's a volatile liquid. What we need to do is we need to reduce it. So this reducing agent here is potassium naphthalide. We all know what naphthalene is, I hope? Yeah. So if you react naphthalene with potassium, then it does react giving you potassium naphthalide. Potassium naphthalide is a very potent reducing agent, but has better solubility than potassium metal. So it has some advantages over potassium metal. Very effective reducing agent for transition metal species. So you can then do this reaction on the 1 bar of carbon monoxide pressure. And here we have to use this species 15 crown 5, and that's there simply to wrap around the potassium ions. Do we all know what 15 crown 5 is? Did actually tell you last year. So 15 crown 5 is a crown ether. So if you draw 5 oxygen atoms like this. The easiest way to draw these crown ethers, I find, is like that. So the 15 comes from the number of species in this ring, and the 5 comes from the number of oxygen atoms. And the beauty of this species is it's just the right size for potassium to sit in the middle. So 15 crown 5 is added. It doesn't have much of a role in the chemistry, except to make a nice, big, stable cationic species. Because what we're looking at here is a titanium hexacarbonyl dianion, and that's a fairly large anion. And remember, if you want to make a stable ionic compound, you want as good a match as possible between the size of the cation and the size of the anion. That's how to make stable compounds. So that's what happens if you react these together. Now this, of course, I think we've already established, I think we've already done the electron count for this, is an 18 electron complex. Incidentally, you cannot make titanium heptacarbonyl. Titanium heptacarbonyl is, or would be rather, an 18 electron compound. Titanium has 4 d electrons, 7 CO ligands would be 14 electrons. That would be an 18 electron compound. But it does not exist because it's running up to our second consideration here, which is that we cannot exceed a steric number of 6. So the reason, in case anybody's wondering, you cannot have titanium heptacarbonyl is because that's 1 ligand too many here. What about vanadium? Well, convenient starting material for vanadium is vanadium trichloride. Again, we need to add a reducing agent. You don't necessarily have to remember which reducing agent to add. It's the concept that we need to reduce vanadium down to vanadium in a lower oxidation state. And the way that we do that is using sodium metal in a solvent called diglyme. Now, diglyme is again a bidentate ether ligand. So what you're doing is you're just adding an ether ligand that can coordinate to your sodium cation and produce a nice, large, stable cation species to counter your anion. And therefore, the one that we get, because vanadium is in group 5, what we get is vanadium hexacarbonyl monoanion. That's a colourless 18 electron ionic compound. Of course, this is an anion here. What you find is if you protonate this anionic compound, so it's anionic compound, potentially a conjugate base. If you protonate it, what you find is you get evolution, gas given off, and that gas is hydrogen. So if you protonate this compound, you get vanadium hexacarbonyl. And vanadium hexacarbonyl, don't have to ask you, I guess I've told you, is a 17 valence electron compound. And since it is a 17 valence electron compound, we predict it to be very, very reactive and unstable. Now, you might say to me, well, it's a 17 electron compound. Why doesn't it form a vanadium-vanadium bond, just like some of our later examples will do? Well, again, the problem that we have here is if there was a vanadium-vanadium bond, then that would be a 7-coordinate compound, and we can't exceed 6-coordinate. So vanadium hexacarbonyl does not have the option of dimerizing to achieve an 18 electron count. What you end up with is a species that is very, very sensitive towards itself being reduced. Now, if a compound like this is very easily reduced, how will it behave towards other compounds? Yes. So this will be a potent oxidizing agent because there is such a strong driving force to become an anion, which would be an 18 electron species. So it's a strong oxidizing agent. A few more examples like this. So you can reduce chromium with aluminium metal, or chromium trichloride with aluminium metal under a high pressure of carbon monoxide. That will give you chromium hexacarbonyl. Chromium hexacarbonyl is an octahedral 18 electron compound. So it fits very nicely in with the trends in our organometallic and transition metal chemistry generally. It has octahedral geometry and an 18 electron count. And it's colourless and air stable because it's essentially both electronically saturated, it has 18 electrons, and it's sterically saturated, it has 6 ligands around it. So it is, as we predict, really a very stable compound, chromium hexacarbonyl. What about manganese? Well, in the case of manganese, we've got a convenient manganese acetate starting material. If you reduce that with triethyl aluminium in isopropyl ether, these conditions are the genuine ones from the original syntheses here, then you eliminate aluminium acetate, and what you produce is dimanganese pentacarbonyl. Now, what structure would you predict for dimanganese decacarbonyl, of course? There's manganese pentacarbonyl dimer. So what structure would you predict for dimanganese decacarbonyl? Yes, it's going to be a dimeric compound, which we encountered in the previous lecture. But what we have to remember here is it's not like the cobalt case. This case, you have a dimeric compound where you have a manganese-manganese bond and you have 5 terminal CO ligands. So in the case of cobalt, we had the option of having either terminal or some bridging carbon monoxide ligands. There will be no bridging carbon monoxide ligands in dimanganese decacarbonyl, because if there were, you would exceed a steric number of 6, and that's not going to happen. So we don't have the same choices of possible structures in that case. And this one you've already seen. So dicobalt octacarbonyl exists as 2 different isomers, 2 genuinely different compounds depending on whether or not you have bridging or terminal CO ligand. Now, there's something special about carbon monoxide complexes, certainly something special about carbon monoxide complexes in the context of the transition metal chemistry you've done so far on Chemistry 2C32. Because what we've just been looking at, if we think about the chromium compound, the nickel compound, the iron compound, the cobalt compound, the manganese compound, less so, well, they were all in oxidation state 0. All of those compounds contain the element, the metal, in oxidation state 0. In the case of vanadium, we saw the element in oxidation state -1. And in the case of titanium, the oxidation state of titanium was -2. Now those are oxidation states you haven't encountered so far. You won't see oxidation states like that if you're using classical ligands like ammonia and water. They just don't exist. If you're going to have classical compounds, then what you need is a strongly Lewis acidic transition metal center, and that tends to mean a transition metal center in an oxidation state of 2 or higher. So a classical compound would be like the one between nickel 2 cations and ammonia ligands. That's a classical transition metal complex. What you never find is a compound that looks like this. There is no tetraamine nickel or nickel tetraammonia. It doesn't exist. It isn't a stable compound. And yet we've just seen nickel tetracarbonyl is a stable compound that forms very readily, and we can distill it and use it to purify nickel. So there's a fundamental difference here between carbon monoxide and the kind of classical ligands that you've encountered so far. So what's going on? What is it about carbon monoxide? Is it that carbon monoxide is a superbase with a really good lone pair of electrons that sticks on a transition metal very effectively? Well, let's have a look. Actually, no. It absolutely is not that. Carbon monoxide is a very weak base. How do you test whether something is a very weak base? Well, you try and protonate it. Carbon monoxide is very difficult to protonate indeed, and if you do protonate it with a very strong acid, what you're making is a formyl cation, and that compound is itself inherently unstable. So this formyl cation can be observed spectroscopically but doesn't hang around very long, isn't an isolable kind of compound. So it isn't a spectacularly good base. And yet it's capable of forming these adducts with 0 valent metals. So what is special about carbon monoxide? Well, let's take a look at our old friend, the MO diagram for carbon monoxide, and see if it can give us any insights into what chemistry might be taking place. Right, what do we call this orbital here? The orbital with the highest energy that happens to have a pair of electrons in it. The highest occupied molecular orbital, which is often abbreviated to the HOMO. So the HOMO here is a pair of electrons in a sigma star. It's sigma star with respect to, so it's anti-bonding orbital with respect to the carbon-oxygen bond. But if we look at it here, essentially this orbital has an awful lot of carbon S character in it. So if you were to draw a Lewis diagram of carbon monoxide, then the pair of electrons that is left on the carbon, that's essentially the one we're talking about here. This is a lone pair of electrons on the carbon atom. For the simple organic chemist like me, this is a pair of electrons on the carbon atom, and that's our HOMO. So that's the pair of electrons that is donated to a transition metal in the classical sense as a sigma donor. So this can react as a sigma donor because it has a pair of electrons here. Let's look a bit further in this diagram. What about this level? These are the molecular orbitals of the next highest energy that don't have any electrons in them. What do we call those? So this is the lowest unoccupied molecular orbital. This is the LUMO. So that's the HOMO, and that is the LUMO. And the LUMO are pi star orbitals. They are pi star orbitals. What do you know about the pi star orbitals in carbon monoxide? What shape have they got? Okay, I think I know what you mean. So if we've got a carbon monoxide species like this, what you're going to have is a sigma bond. So this is our sigma bond between the carbon and oxygen. You're going to have a pi bond between the atoms, which has molecular symmetry like this. How many pi bonds are there in carbon monoxide? Two. Where's the other one? Yes, so the other one is difficult for me to draw without obscuring my diagram because it's going to be orthogonal to this one laying in front and behind the board. So that's a sigma bond. These are pi bond. So what does the pi star orbital actually look like? Some dots. Well, remember, this is not much different to the pi star orbitals that you've drawn for alkenes many times in your organic careers. So what you're going to have is a lobe of electron density here and on here. And of course, we need to get our phase right. The phase is critically important when you're drawing these diagrams. So here we've got constructive interference of these species. Here, of course, we've got destructive interference. So the phase of our pi star orbital looks like this. And of course, there'll be another one looking just the same, sticking in and out of the board. Now we have, as we've recognised before, and I wish I had a different colour here, we have a lone pair of electrons on the carbon monoxide which is able to donate to our transition metal centre. So this is our sigma donor ability of our carbon monoxide ligand. Now, actually, if we're dealing with an octahedral geometry, okay, so let's say we're talking about chromium hexacarbonyl here. So this is chromium hexacarbonyl. It's an octahedral geometry, and so these CO ligands, which d orbitals are they donating into? By tradition, essentially your ligands are going to come in along the axes here. So let's say, for example, I don't know, which axis do you want this to be? The Z. Okay, so we imagine it's almost a diatomic species, and we've got a Z axis here. In that case, if this is the Z axis, normally see Z up the board. This is the Z axis, and I'm happy to go with that. If that's the Z axis, which metal orbital is it donating electron density into? Actually, the original answer I was looking for, those people who said dz squared and those people who said Eg, of course, are both right. They are both right, because dz squared is one of the Eg orbitals. So essentially, if you arrange your ligands in an octahedral fashion around the transition metal, then the electron density is being donated into the Eg set. Just two orbitals lying dx squared minus y squared and dz squared. So if this is dz squared, as it must be along the z-axis, then that's the orbital that looks like this. Okay, so I'm not very good at drawing this. I'm not Dr. Jaiser here. So we've got this orbital here. Okay, so this is the orbital that is accepting electron density from the metal here. Now, if I draw, this is getting a bit cluttered, so I'm going to draw another diagram here, and this time I'm just going to stick with my anti-bonding orbitals on my carbon monoxide. So here we have our lone pair along here, but I'm not going to draw that in. We've drawn a dz squared orbital. Now, are there any other orbitals which have a z component? Yeah, dxz anymore? dyz. So we haven't decided what, that's y, okay? So this is y. So what we're going to draw here is dyz. Now, what shape has dyz got? It's in the yz plane, yes? Yep. Okay, so this is dyz that I've drawn. What have I missed out? And the students miss out all the time. The phase. And the phase, if we're going to be bonding these two species together, must be the same as the phase in the orbitals that I want to overlap it with. So that is the phase of these orbitals. Now, what can you tell me about the pi star orbital? Does it have any electrons in it? No, it doesn't have any electrons in it. What's special about 18-electron organometallic compounds? Where do we fill up to in our molecular orbital scheme? We fill up to T2, up to and including T2G. So the T2G orbitals, which would include dxy, dyz and dxz, are full of electrons. So now we have a situation where we can donate electron density from our occupied metal orbital into our unoccupied pi star orbital. And so this direction of bonding is classical bonding, where electron density goes from the ligand to the metal in a classical direction. This is where the ligand is acting as what's known as a pi acid or a pi acceptor species, because it is accepting electron density with pi symmetry, in an overlap of orbitals with pi symmetry. And this process is known as back bonding. It's called back bonding because the electron density is going backwards from the direction we normally expect ligands to go. Electron density is flowing from the transition metal into orbitals on the ligand. And if you think about it, these two processes are actually synergic. They act together because what we've got is electron density being donated but from the lone pair into the metal and then coming out of the metal and into the pi star orbitals. So what you end up with is a situation where the bonding interactions are stronger than they would otherwise be because they're actually acting to reinforce one another in these systems. So that's essentially, I've gone through on the whiteboard what we have on this slide here. So we have two bonding interactions. We have a so-called dative bonding interaction, which is the one you've seen to death in classical coordination chemistry. And I know Dr. Claydon has also talked about ligands acting as pi acceptors. And this is a slightly different way of thinking about it. This is through overlapping the orbitals on the transition metal and the orbitals on the organic ligand. And what you get is back donation of electron density. Both of these are required to explain the stability of carbon monoxide complexes. And if you think about this back bonding concept, this is why it is lower oxidation states, 0 or even negative oxidation states, that are the most stable carbon monoxide compounds, because those have got the most electron density to back donate into the pi star bonds. That's why you get compounds in these lower oxidation states. Okay. Now, if you start occupying pi star bonds on a ligand like carbon monoxide, that does not go without consequences. If you start populating anti-bonding orbitals, you are going to change the strength of the carbon-oxygen bond. Hope that follows. If you occupy an anti-bonding orbital, you are going to weaken the bond. And you can spot this weakening of the bond occurring in metal carbonyl compounds. And you can spot it very easily through looking at the infrared spectra. And in here, we've got different bonding modes of carbon monoxide. So if we consider our cobalt compounds that we actually coincidentally, because someone nominated them, started this lecture with cobalt carbonyl compounds. Cobalt carbonyl turns out to be a really good example for looking at CO stretches because we have two possible isomers here. And what you find is that you get a range of different carbon-oxygen stretching frequencies in these compounds. But one of these compounds has carbon-oxygen stretching frequencies at 1886 and 1857 wave numbers that is much lower than the other compound. And the reason for that is because this compound has bridging carbon monoxide ligands. Now, why should bridging carbon monoxide ligands have much lower values of stretching frequency than terminal carbon monoxide ligands? Why is that? Yeah, you're right. Carry on. They have got two metals. That's the definition of a bridging ligand. Why would that lead to a lower stretching frequency? And what we're looking for here is to actually tie all of these pieces of information together to construct a logical argument. So why is a bridging CO ligand observed at a lower stretching frequency than a terminal CO ligand? Because it is bonded to two different transition metals. If it is bonded to two different transition metals, it is receiving back-donated electron density from two different transition metals. Therefore, it is receiving more back donation. More back donation means more occupation of pi star orbitals. More occupation of pi star orbitals means weaker carbon-oxygen bond strength, and weaker carbon-oxygen bond strength, as we'll see on the next slide or so, means lower stretching frequency. And that follows entirely logically for essentially the weaker a bond, the lower its stretching frequency will be. That's not unique to carbon monoxide by any stretch of the imagination. So what you find is that you can, in neutral compounds, essentially tell what sort of CO ligand you have based on looking at the IR spectrum. So if it is free carbon monoxide comes at 2143 wave numbers. So if you run the IR spectrum of free carbon monoxide gas, you get 2143 wave numbers. If you coordinate it in a terminal fashion to a transition metal species, then you get a range of stretching frequencies depending on which metal it is and how many of the ligands that we've got, anywhere from 2120 to 1850 wave numbers. So that's typical for terminal. If you've got bridging carbon monoxide ligands, then the stretching frequencies will be lower. So all other things being equal, the stretching frequency of a bridging ligand will be much lower. So we observe stretching frequencies down to 1750 wave numbers here. And if you have a triply bridging species, you get them from 1730 to 1620. Now these kind of stretching frequencies should be familiar to you from what sort of functional group? What sort of functional group in organic chemistry has a stretching frequency of 1700 wave numbers? A carbonyl function. Because, of course, we're starting off with carbon monoxide, which is triply bonded. But we are populating those antibonding orbitals to such an extent that we are essentially moving from a triply bonded species right through to a doubly bonded species, and in some cases where the bonding more closely resembles a singly bonded species because of the extent of occupation of those pi star orbitals. So essentially we can use this fact in order to distinguish between different species. So if we have two different isomers like we had in the case of cobalt, the one with the lowest stretching frequency is going to be the one with a bridging carbonyl ligand. However, there are other factors that can affect the extent of back bonding. So the more metals your carbon monoxide ligand is bonded to, the more back bonding it experiences. However, there are other ways of varying the amount of back bonding. So if we talk about an anionic compound, so if we have a compound that is carrying a formal negative charge, it is clearly more electron rich, a neutral compound, and therefore it has got more electron density to back donate into pi star orbitals. So if you have anionic carbonyl compounds, they will have carbon-oxygen stretching frequencies that are lower than neutral compounds. And it would also follow that if you had a cationic compound, would you expect its CO stretching frequency to be higher or lower than a neutral compound? So if it was cationic, it will be higher, yes. A cationic compound would have a higher stretching frequency than a neutral compound. Why? Because it has less electron density. Less electron density means less back bonding. Less back bonding means less occupation of pi star orbitals. Less occupation of pi star orbitals means a stronger carbon-oxygen bond, and a stronger carbon-oxygen bond stretches at higher frequency. I know this argument gets a bit pedantic, but that's what I'm trying to equip you to do. Not just to guess up, down, left, right, but to be able to string these facts together and create a logical explanation as to why these things are actually occurring. And the beauty of CO stretches, of course, is worth saying, because there is such a dipole change associated when a carbon-oxygen bond stretches, they give very strong signals in the infrared spectrum. And they also give signals in the infrared spectrum where nothing else comes. So following carbon-oxygen stretches in the infrared spectrum is a very satisfactory way of studying chemical processes, because it comes in a part of the spectrum where nothing else tends to be occurring. And that's essentially what many of you, about 2/3 of you, already done that now, studying topic 1 in the 2C32 practical course. That's exactly what you do there. So let's have a little bit of spectroscopy at this point. Hopefully this equation here is not going to be unfamiliar to you. So you will recognise this equation here, essentially that the frequency, which is given the Greek symbol nu, is proportional, and as I said, I might have said before, this is actually alpha. This is genuinely not a typo. This is how alpha looks in the Comic Sans font. But this is nu is proportional to the square root of k divided by m, where this should essentially really be mu m, the reduced mass. And k is our force constant. And of course it is k that is a measure of the strength of the bond. So it follows immediately from this equation here, if you weaken the bond and keep everything else constant, then the species will stretch at a lower frequency. That follows from this equation here. So just to summarise here, extensive back bonding is going to lower the carbon-oxygen bond order. And if you lower the carbon-oxygen bond order, this equation here is telling you that will lower the stretching frequency. If the compound is positively charged or contains strongly electron-withdrawing ligands, so we haven't talked about a lot of ligands so far in this course. If you have a ligand that is very good at electron donating, it will increase the electron density at your metal centre. If you have a ligand which is good at electron withdrawing, carbon monoxide being a good example of a ligand that is good at removing electron density from the metal centre, that will have the effect of also reducing electron density at the metal centre. So you can either have a cation or you can put on electron withdrawing ligands. Both of these things will decrease electron density at the metal. And if you decrease electron density at the metal, as we've said, you decrease the potential for back bonding, you decrease the occupancy of the pi star orbitals, and you make the carbon-oxygen bonds stronger and the CO stretch higher. Okay, let's have a look at some more examples of these compounds here. Now, carbon monoxide gas has a stretching frequency of 2143. Now, if I coordinate carbon monoxide gas to a Lewis acid like BH3, not a transition metal, but a Lewis acid like BH3, look what happens. There's no weakening of the carbon-oxygen bond. If anything, apparently the carbon-oxygen bond seems to get stronger. Why is that? Cast your eyes back on that molecular orbital diagram. Of carbon monoxide, can you use it to explain why, if you use a pure Lewis acid, which cannot back donate electron density, i.e. BH3, why does that lead to an actual increase in the CO stretching frequency? Yes, if you look at that MO diagram, that lone pair on the carbon is anti-bonding with respect to the carbon-oxygen bond. And if we remove electron density from that anti-bonding orbital, we are effectively strengthening the carbon-oxygen bond. So if you just have a pure Lewis acid, one that cannot do back donation, you actually observe an increase on coordination of these species. Now, let's take a series of, this is a series of isoelectronic compounds. What does isoelectronic mean? They have the same number of electrons. So these compounds here have the same number of electrons. They are all 18 electron compounds, but they are carrying different formal charges. So this is hopefully consistent with the pattern that you would have expected. As you increase the formal charge on the metal, what you are doing is you are increasing the electron density at the metal. And as you increase the electron density at the metal, do I have to say it again? It occupies the pi star orbital to a greater extent and weakens the carbon-oxygen stretch, and so we see lower stretching frequencies. So this is just as we expected, going from neutral species to anionic species, all with the same number of electrons, but with different carbon-oxygen bond strengths. And exactly the same but opposite trend is observed if you go from a neutral compound to a cationic compound. So just as we predicted, going from these isoelectronic chromium hexacarbonyl to manganese hexacarbonyl cation, we observe an increase in the CO stretch because there is less back bonding in that system. So just to summarise here, essentially, if you can remember 18 and 6, then you don't have to learn all those infernal metal carbon structures. I honestly believe that you can predict all of these structures. How do you make them? Well, a general method here is obviously to take a metal salt and a reducing agent in the presence of carbon monoxide. That allows us to make these species. And then essentially, if we use a bit of common sense, that what will change the electron density on the metal and recognise that what's happening here is back bonding, then you can predict the CO stretching frequencies of your compounds to pretty good effectiveness simply by recognising what the electron density on these compounds will be.